In this video, we will discuss how to write an embedded C program to find the sum of two matrices. Okay, here you can consider two metrics. We can indicate this is matrix 1 and this is matrix 2. And it's a 3 by 3 matrix. And here also it's a 3 by 3 matrix. So make sure that two matrices are the same dimension. And in the matrix addition, you can see the first element of matrix 1. For example, this is indicated as mat 1. So the first element is we can access like mat 0, 0. Okay, mat 1. And for the second matrix, this is mat 2, 0, 0. So the first element of the two matrices will be added. And here you can see the value is 1 and here it is 9. So it will be added. Similarly, each element will be accessed. It's a 3 by 3 matrix. So the index value starts from 0 and 3 rows and 3 columns. So this is a normal case. Now we need to implement this concept in a embedded C program or very specifically for 8051 microcontroller. And in the case of microcontroller, we can store the values in internal RAM or external RAM. In this particular example, we'll discuss how we can store matrix values in external RAM and we can access that. So the external RAM address starts from 000H to f of x. And assume that the matrix 1 and matrix 2 are located at the external RAM location. Okay, it's all about the initial assumption. Now we'll discuss the theory part. And for example, to perform this particular program, we need two matrices. So one matrix is indicated as match 1 and second one is indicated as 2. Okay, and we need to store the result in another matrix. So that matrix is indicated as result, RE. Okay, and this is a usual notation that used in a C program to access each element of matrix, I for row accessing and J for the column. So matrix 1, I and J. So I indicating the row and J indicating the column. So this is a usual notation to access matrix in C program. And the index value starts from 0 onwards. So this is 0, 1, 2. Here is a 0, 1, 2. So this is the row, and here it is I, and here it is J. Okay. And the same index variables we can use for accessing the second matrix also. And in embedded C program, usually we will use the pointer notation to access the matrix or array. That's a usual practice. So instead of using this particular notation, mat1 I, j, we can use the pointer notation. And in order to access the result ij, instead of that, we can consider the pointer notation. This RE is actually indicating starting location of the matrix. So in order to access the first row, we can use or the row, we can use this particular syntax res plus I star. Okay, this is a pointer which is pointing to the first row, and we need to access the column element. So we can use plus J and pointer. Okay, so this particular notation will access, or it is equivalent to res within the square bracket I and J. Okay, so in embedded C program, usually we will use the pointer notations, and if you want to use pointers in your program, you can use this particular syntax. So either you can use this matrix, two-dimensional matrix syntax, or this pointer notation. So now we'll give you more idea about the memory location and all. Assume that this is a usual format to store the matrix, and assume that it's a 3 by 3 matrix, and the name of the matrix is matrix 3 by 3. So 3 rows and 3 columns. And assume that the array values, actually here we can see there's a row and column format, but in actual case, all these values are stored in a consecutive memory location. For example, if this location is 200, the first element is stored in 200, and you assume that all these values are 8-bit values. So next location is 2001, 2002, 2003, 2000, sorry, not 2000, 204, 205, 206, 207, and 208. So you can see that when you write the matrix, it will be like row and column wise. But when you store the values inside the memory, it will be in a consecutive location. So first, it will store the first row. After that, the second. So the first three indicating the first row values, and here onwards, the second one. So I think I made it. No, it's a 3 by 3. So 0, 1, 2, and next three values, and the last one. So this is actually row 1, and this is row 2, and this is row 3. Okay. And in order to access the first row, you can use the pointer notation like this: matrix plus 0 star. So this notation is actually pointing the first location or the first row, that is 200. Okay. And if you use this notation, matrix plus 1 is actually pointing to the second row, starting address of the second row, that is 2003 in this particular, not 2000, it's 203. And if you use matrix plus 2, it's actually the starting address of the third row, that is 206. Okay. And if you want to access a particular element within that row, in the first row, so we can use star matrix plus 0 is actually pointing the first row. And if you want to access the first element of the first row, you can use plus 0. Okay. And if you enter the second element, you need to add plus 1, plus 2. So this, all these plus 1 and plus 2 perform the address addition. So if the matrix is declared as character, it will add plus 1 by location in the case of embedded C program. And if you use integer type, each plus indicate 2 byte location. So there will be difference if you declare the variable. Depends on the data type, the memory address will change. Okay. So here it's the character type or 8-bit byte. So that's why plus 1 will point to the next location. Okay. This is all about the matrix notations in pointer concept. Now, here also explain the same thing. See, the keyword matrix in this particular example is actually pointing the base address of the two-dimensional array. Okay. And if you use star matrix, point the first row of the two-dimensional array, plus 0 also you can use the same thing. And if you use star matrix, point to the matrix 0, 0. Okay. And the same notation you can use in this way also, star within the bracket star matrix plus 0. So that already explained in this particular example. Okay. Now there's one problem: how to declare a two-dimensional array. There is 2D array or a matrix. 2D array or a matrix. So matrix can be considered as a two-dimensional array. So collection of one-dimensional array. So in order to point or in order to declare matrix or a two-dimensional array using pointer, we will use this particular notation. So we need to declare data type and pointer symbol, then variable name and size of the array. That is the row size. So if you want to declare this particular matrix, and you can see that each row contains 3 elements. Okay. So you can declare, for example, here you can see that mat1 3 means actually indicating it will declare an array of pointer to an array. Okay. And the 3 is actually indicating it's a 3, here it is character, so it's a 3 byte wide array. So this is actually indicating a one-dimensional array pointing to the one-dimensional array, and the array size is 3. If you simply declare mat1, it's actually pointing a character type pointer. Here it's a 3 byte wide array you can declare by using this. So if you perform a plus to this particular quantity, it will point to the next row. Okay, when you write the program, you will get more idea about that. So we can declare a two-dimensional array or matrix by using this particular concept. Now we'll see how we can write the program to perform the addition, and we'll simulate that particular program in a compiler. Here you can see the usual program, how we can write a embedded C program to add two matrices. So here you can see that matrix is declared in a usual way. Two matrix, there is a matrix or a two-dimensional array with 3 rows and 3 columns. And here also you can see match 1 and match 2. So 3 matrices are there to store values, and final result is stored in SL. And we will use external data memory. That's why this keyword X data. And we will use only 8-bit value in this particular program. That's why it's a character unsigned character type. And we need 2 variables to control the loop, so that we are using 2 variables I and J. And here you can see 2 loops to access the matrix. That's the usual way. And here you can see how we can access matrix without using any pointer control. Okay, but if you run this particular program in embedded C concept, you can see that the final result. So we are accessing the X data view here and data views here. If you run this particular program, see, we don't know where the values are actually stored. Okay, so in external memory, somewhere this compiler will allocate some memory location. So in this particular example, if you look at this res is actually allocating from this particular point onwards. Okay, so that is 1 0 1 1 1 2. Okay, so 1 2 onwards is actually allocating a 3 by 3 matrix. So this highlighted portion, and so match 1. If you look at this match 1, you can see that it's starting from 9A, so 9 locations again allocated. But all these allocations are done by the compiler, and there is no control for the user side or programmer side. So all these values are consecutively allocated from first location onwards. So it will declare the first match 2 from 0 onwards. After that, it will declare another matrix as match 1, and finally the result. Okay, in the compiler, it's automatically done based on the internal logic. But when you write the embedded C program, sometimes we need to specify the values or location. So instead of that, we need to start from 200 onwards or 300 onwards. In that particular case, we cannot use this particular program. Okay, but to solve that particular problem, we need to allocate some specific locations. We use another concept, and this is a usual program. So I will explain the other one. This program assumes that the matrix values are stored with some random values. So if you run this particular program, you can see the final output is A, because if you perform the first element 1 plus 9, it's actually 10. So in hexadecimal it's A. That's why all elements are loaded with A, etc. So this is a usual notation. Now we'll discuss another program where we will use the pointer concept to explain the program. So here we are declaring the matrix in the pointer concept, the pointer to an array. Okay, so here the matrix or array is declared as the row or one-dimensional array is pointing star res within the star bracket right. Okay, it's actually pointing to a 3 element array or a row. Okay, similarly next matrix and matrix 2. So if you use this particular notation, we can specify the starting address of the matrix or array. For example, the match 1 is allocated with a 1 0 means we can store the value, or we can specify the starting address of the matrix 1. In the previous case, it is automatically done by the compiler. In this particular example, the compiler is automatically assigned. Here we can specified address. So matrix 1 is from 10 onwards, matrix 2 from 20 onwards, and the result is from 30 onwards. To access a specific location or to store the value in a specific location using matrix concept, we need to declare each matrix in this particular way. And this is actually a pointer which point to an array. Okay. And the remaining thing you can use in the usual way to loops I and j to be change the variable. Result I j is equal to matrix 1 matrix ij plus matrix 2 ij, and we'll see how we can access the value. So here this is a location 10, so we can store some value from here onwards. So 1 2 3 4 5 6, and the second matrix is actually we are starting from 20 onwards. So this is 20 location. So we will add 1 in each location. And you can see that the result is actually stored in a 30 onwards. So 30 is initially ordered with FF. Now we see how the program will execute. So you can see that after addition, the first location content is 1 and the second matrix is 1. So 1 plus 1 is 2. And you can add 2 plus 1, 3, 3 plus 1, 4, etc. So in this particular case, we can specify the memory location. 9 plus 1, it's 8, okay, or 10. Okay. So this is how we will access matrix using the pointer concept. Now we'll discuss one more problem, how we can use the pointer concept in this particular statement also. So here we are using the matrix notation. Now in the next program, we will see how we can use the pointer notation. Okay. So here again you can see that the previous statement is now changed to in the pointer concept. So instead of using the matrix notation, here we will use the pointer notation which we explained in the theory part. Instead of using result ij, we will use the pointer notation. And if you use this particular notation, you will get the exactly same result. And here you can see that matrix is also declared as a pointer by using the pointer concept. So matrix 1 plus matrix 2, 10, 20, 30 as a static location of the matrix. So if you perform the operation, you can see that same result we will obtain in this particular case. Okay. So in this way, we can access the matrix. Okay.